Swayam Prabha. Digital India. Educated India.
So in the last class, we had started talking about natural modes of rooms. We had started with one-dimensional rooms, basically very long ducts. Then we had talked about 2D rooms, and I think we also covered 3D rooms. We did not cover 3D rooms. Okay. So we will recap a little bit of that, and we will extend the same analogy to 3D rooms today. And we will also introduce slightly new concepts also. So for 1D rooms, we had said that the natural mode and the associated natural frequency, let's say it is Fn, is basically n times c over 2l, where l is the length of the room, c is velocity of sound, and n is as an integer number. And I can represent this in a vector form like this. So this is my frequency, this is my origin 0. So the existence of a node is after every period distance or unit distance, where a unit distance is c over 2l long. So every c over 2l I have a node. F3 for instance will represent this is F3. So the third natural frequency of this room will be F3, where F3 is defined as frequency associated with 3c over 2l. In terms of wavelength, each of these units is lambda over 2 in the direction of the length. So that is for one dimension. So now we will extend similar thought process for 2D rooms. So in case of 2D rooms, the frequency is associated with an x direction parameter and a y direction parameter. So f n x and y equals c over 2 nx over lx squared plus ny over ly squared. And we had also shown that the angle of incidence of nx and yth mode or natural frequency of the room has to be tan inverse of ny times lx over nx times ly. And based on this understanding, we had shown some natural modes of rooms. Let's say I have a room, it's a two-dimensional room, its dimension in y direction is ly, dimension in x direction is lx. Then there could be a crisscross pattern of nodes and crisscross pattern of nodal lines in the room, and the boundary condition, the number of nodes in y direction is essentially ny, the number of nodes in x direction along the length of the room is nx. So that is the physical interpretation. Also on each line, let's say I consider this particular line, I'm just highlighting it and making it thick. So along this line, my normal velocity Vn is 0, and that is basically because the boundary condition at the point where this line hits the wall. If I have one node line going in this direction and another node line going in this direction, then these two lines, the velocity condition will be Vn1 equals 0. Let's say this is line 1 with a normal n1, and Vn2 equals 0 for this line which has a normal N2. These lines don't have to be necessarily at right angles to each other, because essentially these are reflections. So at point of intersection, this is my velocity condition. Vn1 is same as Vn2 is equal to 0. If the angle of intersection of these two lines is 90 degrees identically, then the total velocity is 0 at the point of intersection. We had developed this kind of a concept for a 1D room. We'll represent similarly in 2D space the frequency of a two-dimensional room, and we do it in this way. So I have an x and a y coordinate system. On the horizontal axis, I am plotting f of cosine theta, and in the vertical direction, I am plotting fy sine of theta, where theta, as we had explained in earlier class, is the direction of the incident wave. This is my x-axis in a room, this is my y-axis in a room, theta is the angle of incidence. So just as in this case, we had put a unit length as c over 2l, if I extend this analogy in two-dimensional space, what will be the unit along the length direction, x direction? C over 2 Lx, right? And in the vertical direction, C over 2 Ly. 3 or 4 lines. And you'll have to bear with my not such a good drawing. Okay. So this is C over 2 Lx, where Lx is the length in x direction for the room. C over 2 Ly times 2. This is 4C over 2 Lx. This should be x. And this is 3C over 2 Lx. Similarly, in vertical direction, I have C over 2 Ly, 2 times C over 2 Ly, 3 times C over 2 Ly, and so on and so forth. So the natural frequency of a room will be any intersection point of these two of the grids. So this could be a natural frequency, this could be a natural frequency, this could be a natural frequency. This is not a natural frequency, this point. It's not a natural frequency because there is no intersection. So for instance, if I consider this point, E, then this is f 1, 2, 3, 4 in the x direction, 4, 3. Similarly, another natural frequency could be f 4, 2. So for 4, 2, I can write the relation as four times C over 2L. Basically, the length of this vector is the magnitude of the frequency. So it is 4 times C over 2Lx whole square plus 2 times C over 2Ly whole square, the square root of the whole thing. And the angle of incidence associated with 4, 2, which has to be maintained to create this mode in the room, is theta, and that is essentially tan inverse of this component divided by this component. So it's 2c over 2Ly times 2Lx over 4c. I take the inverse tangent of it. So once again, this is my f42, this is it's 43, and this is f42. So essentially we have extended this kind of a representation to two-dimensional space. for 2D rooms. So now we take the next jump and we go to 3-dimensional 3D rooms. So you can have a room it could have a height, width and length. Again, these are rooms with parallel walls. All this analysis is assuming that the walls are parallel. So this could be my x-axis, y-axis, z-axis. The dimensions along x, y and z are Lx, Ly, Lz. So if I draw a 3-dimensional coordinate system and put a point in it, right? So I have a point P. This is my z-axis, y, x. I make an angle phi with respect to the z-axis of this vector, and in the xy plane, the projection of this vector P, vector OP, is OP prime. And OP prime makes an angle theta with respect to x-axis. So this is standard 3D Cartesian geometry. Such a system, what will be the natural frequency for a room? If I use similar approach, is basically you add one more term here, right? Nz over Lz whole square. So F, Nx, Ny, Nz equals Nx over Lx square, Ny over Ly square, Nz over Lz square, the whole thing we take a square root of, times C over. And the way we express this frequency in 2-dimensional space for 2D rooms, we will use a similar approach to figure out the value of theta and phi in 3-dimensional space for 3D actual rooms. So this room is more or less like a 3-dimensional room. It has a little bit of projection, non-rectangular structure there, but otherwise more or less a 3D room. So what I do is, now I represent this f, nx, and y in 3D space. So this could be a point P, and if this point P is located at an intersection point of C over 2 Lx, C over 2 Ly, C over 2 Lz lines, then it is a node and it's a valid frequency, right? Similarly, like we developed for 2D. So it has to reside at the node points, at the grid point of these parallel, these lines. It has to lie at the intersection of these lines. So in this case, I have to extend it a little bit. So my vector OP equals F. What will it be? This is my y-axis, x-axis, z-axis. So this is C over 2 Lx, Ly, twice, thrice 4, and so it could be 4, 4, and in the z direction I have 3. 0 what? I have to draw a better picture to show it in 3-dimensional space. It appears. But the point is that it is sitting somewhere which is 4 times c over 2 Lx along the x-axis, 4 times c over 2 Ly along the y-axis, and 3 times c over 2 Lz in the z direction. That is the location. So maybe you can draw a better picture, but that is what I am trying to show. And from this kind of a representation, I can figure out tan theta. So tan phi is, man, can you help with what is the value of tan phi in this case? Well, I mean tan phi, okay.
Oh, tan phi you have to.
Huh.
So then, and
In the z direction, it's 3 times c over 2
yes,
Lz.
y direction should be looking first.
And
Y direction.
the
So,
projection of it in the x y plane will be,
so first we should take projection in the y direction because you have defined phi with z axis.
huh,
So then first term should be projection with y axis.
in the xy plane.
No, sir. In the diagram you have defined tan phi. Phi is the angle with the z axis.
Yes.
So then the y term should be taken. The z term should come at the denominator. And z over.
Yes. So it will be in the denominator. It will be 3c over 2 Lz, right? And in the numerator, it will be 4c over 2 Lx plus 4c over 2 Ly. This entire thing, right? And tan theta is basically 4c over 2 Ly times 2 Lx over 4c. So you have a process and an approach through which you can locate the physical nodes of different frequencies for a given 3D rectangular room. You find out its coordinates, and for each frequency, in a very methodical way, you can say that, oh, this is a node, this is a node, this is a node. So at the nodal lines, my pressure is minimum or maximum at points of where these things, intersections are happening. It's maximized, right? And my velocity is minimized. These node locations vary with respect to each frequency. So the challenge is that if there is a room where there are lots of nodes, big band of frequencies, what does that mean in terms of perception of sound? That as person moves from one place to other, he will see big changes in the volume related to a specific frequency. So his understanding of sound or his perception of sound will change from place to place as he moves from one place to other place to other, and so on and so forth. So that is not a good room to have, right? Where some place he will see a higher level of SPL, then he moves to an anti-node location where he will have a lower level of sound, then he moves to another one, and so on and so forth. So we have to figure out how to construct a room which does not have this challenge. So that actually is a segue into the next concept, which is related to all these approaches we have developed to figure out what is the location of a node in a room. So now what we will try to do is, we'll try to quantify how many nodes are there in a room. Okay, so we will develop that for a 2D room, and then we will extend it for a 3D room. So in 2D rooms, I'll draw the same XY system. My X is same as F cosine theta, and this is F sine theta. And then I'm drawing a grid. So each of this is C over 2 Lx, 2C over 2 Lx, 3C over 2 Lx, and here I have C over 2 Ly, this is 3C over 2 Ly, and so on and so forth. I want to find the number of nodes in this 2D room associated with the frequency F0. Then what I do is I draw a quarter of a circle with the radius F0. So whatever number of nodes are there inside this circle or 1/4 of a circle, that is the number of nodes this room is going to have, right? Area of circle, actually 1/4 area of circle is pi F0 square over 4, and area of one of these guys, these rectangles, is what? So number of node is how much? I just take the ratio of these two. So pi F0 square over 4 times 4 Lx Ly over C square. What do I get? Pi F0 square over C square times Lx Ly, and this is pi F0 square over C square times area of room. I can make this generalization to area of room only if it's a rectangular room. Actually, this is a more fundamental relation, Lx Ly. So what this says is that n is dependent on the square of frequency.
So how does it represent number of nodes?
Huh?
How does this ratio represent number of nodes?
It represents how many rectangles are there in this C circle,
So, but
frequency circle.
there's some area left, like, and which will contribute to.
Yes.
Uh,
So this is a very broad estimate, because you will see that at higher frequencies this number of nodes runs into millions. It runs into millions. So you can omit 2, 3, 10, but it's a fairly good representation. It's a discretization of a continuous function. So what this says is that number of nodes is dependent on the square of frequency. As frequency doubles up, number of node becomes 4 times. That is one thing. And obviously, if you have a larger room, you'll have larger number of nodes. If you have a smaller room, you will have smaller number of nodes.
Also, the larger room will have very closely spaced nodes, because Lx and Ly will be large.
This C over 2 Lx,
So almost nodes at all the frequencies, like if the room is larger.
no, the tightness of one node to other, closeness of one node to other will depend on the wavelength.
The Lx and Ly are independent of the wavelength.
Lx and Ly are independent, but what you have here is F0 over C, which is wavelength. If you look at wavelength, then F0 over C is the wavelength. So the spacing of the nodes will not change from one large room to a small room.
So, but the spacing is C over 2 Lx.
This is a representation. This is the actual relation. You have to look at this relation in its totality. What this says is, if you have big area of the room, you have large number of nodes. What this says is F0 over C is basically lambda. If you have to relate it, visualize it in terms of spacing of the room, you can do an experiment yourself, numerical experiment, that what is the spacing of a room, whether if you have a room this big and then you make the half as big as it. And at the end of the day, everything ends up in terms of functions of lambda, because you have a node at the room. Away from that, as I move inwards in a 1D tube, after a distance lambda over 2, I have another node. Then after another lambda over 2, I have another node, and so on and so forth. So the spacing is not changing. What is changing is how many nodes you have in 1D room. So for 3D rooms, what will we do? We use the same approach for a 3D room. So instead of area of a circle, what do we compute?
1/8.
1/8 area. Is what will it be? 4 by 3 times pi f naught cube over 8.
4 not 4 by 3. 4
Area of sphere is 4 by 3, right? Volume.
by
And volume of a brick, I can call it, of unit size in that xyz coordinate system where each dimension is c over 2 lx, c over 2 ly, c over 2 lz. This is c over 2 lx times c over 2 ly times c over 2 lz. Okay. So number of nodes n is basically, I take the ratio of these two guys. What that gives me is pi over 6 f naught cube into 8 lx ly lz over c cube, which gives me 4 pi over 3 f naught over c cube times volume of room. So in a 3D room, the number of nodes explodes as frequency goes up. If I increase my frequency by a factor of 10, I have 1000 as many nodes. In a 1D room, it just is linearly dependent. In 2D rooms, it goes up in a squarish way. In 3D rooms, there is a cubic dependence. So we'll do a very small example. Let's say my f naught is 20 kilohertz. That's the highest frequency which a human being can hear. And let's say Lx times Ly times Lz is 25 feet times 15 feet times 8 feet. So this gives me 3000 cubic feet. And C is, I'm making a very crude approximation, 1000 feet per second. So I can either convert it to SI, or this is cubic, and when I do a C cube, I get feet cube per second cube. So it will, so N is 4 over 3 pi times 20 times 10 to the power of 3 cube over 1000 cube times V room. V room is 3000. So this gives me 10 to the power of 8. There are 100 million nodes in a room at 20,000 hertz. If I bring this down to 2000, this number will become approximately equal to 10 to the power of 5. If I bring this down to 200, then this goes to 100 nodes. So for low frequencies, you will hardly hear change in the sound as you move from one location to another. But at higher frequencies, at very high frequencies, you will hardly hear the change in frequencies also, because the spacing will be very tiny. Yeah, wherever your ear can perceive, you have typically, not typically, always we hear from 2 ears. So if the frequency, the spacing is very tight, this may hear something, this may hear something, and the brain will kind of average it and give you a kind of a mean or an RMS value. But if this spacing from this ear to ear is less than the spacing of the node, then you may hear changes in pressure.
Very big auditoriums, let's say 50 feet, as our auditorium, there would be some nodes for bass as well.
For very big auditoriums, there will be nodes for bass as well. Yes. There are bigger issues in very big auditoriums, which is, we will talk about it maybe in next lectures, reverberation and echoes. But yes, for large auditoriums, you will have change in perception of sound for low frequencies. But for most of these rooms of this size, that is not an issue at all. So very simple math, but it shows you a lot. If I do dn over df, then I get f naught square times 4 pi v room over c cube. So again, I'll just do a very quick example. For this example, for these data, my dn over df at f equals f naught comes to be 15, I calculate 15,000. Okay. So dn equals 15,000 df df. So if I make a 1% change in frequency,
Good.
as change in n, where n is a delta n is a small change, is basically 15,000 times delta f naught, or actually f at f equals 20 kilohertz. So what that means is that at 20 kilohertz, if I increase, again just for a appreciation, if I increase my frequency from 20 kilohertz to 20,001, I get 15,000 extra nodes in the room of the dimension which. If I increase my frequency by 1%, increase in frequency, then extra number of nodes which I get is about 3 million. You can use this relation to compute. So at higher frequency, it's very sensitive to changes in frequency. The number of nodes changes very rapidly. So what we will do now is a very simple experiment. So I have a very basic speaker, and what I will do is, from the computer I will generate two frequencies. The first frequency will be 125 hertz. And what you can do is that when the sound is coming, you can close one of your ears, and you can move your ear like this, that, whatever, and see if you can sense the change in sound pressure level. Then I will stop that and I will play another frequency at 3 kilohertz or 2500 hertz, and then try to figure out whether you can sense changes in sound pressure level. Okay. The other thing is that if I play the sound directly from my computer, it's a very clean sound, but looks like there's some electronic issue. So even if I'm not playing it, and when I run it, there's some background noise, static noise. So you can ignore that.
Volume from the laptop full?
Volume from laptop is full. But for purpose of this experiment, I have checked it. This noise will not lead you to wrong conclusions. So what I'm going to do is, I'm going to maximize this and play the. Okay, so that was 125, and hold your thoughts. So now I will change the frequency, and this is now 2500 hertz. So what did you sense? Did you see, what was the difference when you play between 125 and 2500? Saraswat.
So we can sense in both cases, but for the 125 one, the distance was large. And I had to move my head from here to here.
Okay.
Then also the variation was not much.
Significant.
Yes, sir.
Okay.
And in the
And
other
in,
case it was significant for this much distance, I think.
For that much. So what we'll do is, for this room, this is like a rectangular 3D room, kind of. There is some extra non-rectangularity here. What we'll do is compute the number of modes and see.
But these speakers are not omnidirectional. So do they create a real 3D environment?
Because of reflections and everything, at the end of the day, you will get all the modes which will be developed. What this room has is Lx equals 7.06 meters, Ly equals 7.06 meters, Lz equals 3.12 meters. Okay. So my V room is 155.5 meter cube. So if I compute the number of nodes in this room is 4 pi f cube over c cube 3 times V room. And if I do the math, I got a calculator today after a long number of years, I get 1.586 times 10 to the power of minus 5 f cube. So for a 125 hertz frequency, I get 1.586 times 10 to the power of minus 5 into 125 cube, 31 nodes. And for n 2500, basically I can just multiply this by 8000 and I'll get the same number, right? So it's about 2.48 10 to the power 5 equals 2.48 lakh nodes, or 248,000. Lambda 125 hertz, C over 125 is 2.76 meters, right? So lambda at 125 hertz divided by 2. This is the spacing of nodes in an approximate sense, because it also has to depend on theta, which we are not talking about here, is 1.4. And lambda for 2500 is 0.138 meters. So lambda over lambda 2500 over 2 is 6.9 cm. So the first thing which you may have sensed, which Abhishek mentioned, was that for 2500 hertz tone, he had to move his head very little. And it's directly related to the fact that lambda over 2 is just 7 centimeters, about this much.
Sir, one question which may not be relevant, but sir, how do you generate particular frequency sound from a laptop?
I was browsing the net and there is some website where they have a lot of frequency tones, MP3 files. So I just downloaded 2 frequencies. And Kshitij found some tools which I have not used, where you can actually now input frequency and it will give you that particular tone. So again, to Kshitij's point, what he was saying earlier, for low frequencies, 100 hertz, 60 hertz, 40 hertz, actually I tried playing 40 hertz on this, but it will not, it was not producing sufficient. I could not listen 40 hertz sound on it because it is too small. You've seen that for 40 hertz to have a significant SPL level, first its resonance point has to be low, which we saw earlier. Probably its resonance point is maybe 90, 80, 100 hertz. And second thing is it has to move a lot, or its pistonic area has to be large. It could not generate. Also, I tried playing 125 hertz on this computer and I could not hear anything, just by computer itself. So you can generate the frequency, but you may not be able to hear it unless you have the right speaker. The perception of low frequencies does not change significantly in rooms of this size, or even in larger rooms, because you have to physically move a long distance from one place to other to measure that. Which brings me to the next point, that if I am going to plot the pressure at my ear, right? I am sitting in a chair in a room, someone is speaking or some music is coming out or some noise is getting generated. So my ear is hearing something, and that is P ear, and the source is generating some noise or sound content, that is P source. So if I plot P ear over P source, and in the horizontal axis I am just varying frequency because of some of these effects which you just now experienced. My plot will look something like this. As I move from one node to other node, there will be variation in the pressure. And in a lot of cases, this is about 20 decibels. Let's say this is 20 dB. So the maxima and minima are off by about 20 dB, let's say. And that is basically because if the person is not moving, then for different frequencies, he'll have here different SPL levels, and there will be some frequencies where he will hear the minimum. There will be some frequencies where he will hear the maximum. And that spacing will get tighter and tighter as frequency goes up. You have to draw an exact curve, but basically what I'm trying to show here, it's not sinusoidal, right?
Maybe.
It will be wavy because it's a continuous function. It is a continuous function. It won't be jumpy. Think about this. This is P ear. You can also replace it by a microphone. And a P source could be a radio or a tape recorder or a CD player. So you have a CD player with speakers and everything, and you have a microphone. And then you take from the mic and then you record it, that sound. This CD player could be producing a flat frequency response. And what the mic is going to record will be something like this. Then you play this sound again and you hear it. Then the overall threshold. So the first thing is, in the first step, this will be a flat frequency response, this will be a wiggly frequency response. So even though this is producing sound faithfully, mic is not recording it faithfully, because there are echoes, there are reflections, there's interference, and because of all that, the mic is recording something totally different. When you are measuring sound, this is very important. You may conclude based on this data that your source is producing this kind of a sound, but that may not necessarily be the case. That is why in reality, a lot of times people make measurements in anechoic chambers where there are no reflections. But anyway, going back, so you are recording this. So in next step, your CD is producing this sound, because I am feeding that recording back to the CD. So it's producing this. And then the mic will record from here. This threshold will go down, right? The top will remain same, but this threshold will go down. So it will become like this. Do you understand what I'm saying? So each time you record an original soundtrack, the threshold at certain frequencies will keep on going down and down and down and further. That is the reason whenever you're trying to duplicate sounds, a lot of times it's not directly from what is being heard through a sound system. Rather what is preferred is that you just directly take the electronic output in terms of voltages and record it, if you want to replicate it. But if you reproduce sound, it will also you will also be capturing the impact of reflections and echoes. And that will destroy the original soundtrack totally, if you do this iteration several times. And the more you do, the more corrupted your overall sound recording becomes. And it could be for engineering purposes, it could be for entertainment and all that stuff. So that is something I wanted to share with you. So that's all for today. In the next lecture, we will try to explain a little bit about mufflers, which is a little bit of a jump from what we are doing today. In several lectures back in time, we had talked about Helmholtz resonators, right? We are using a volume and a tube. We could eliminate specific frequencies, or not specific frequency, a specific frequency, or a narrow band located around a specific frequency. So that is Helmholtz resonator. What we'll talk about is a little bit about mufflers, which are used in a lot of automobiles, or all the automobiles, scooters, motorcycles, cars, trucks. How do they work? And then we will also start introducing the impact of echoes, what is a reverberant field in rooms, how can you reduce the impact of reflections in rooms. So that's what we'll cover in next couple of lectures. That's what I wanted to talk about today. Thanks.